Hello friends, in this video I will be talking about that is bias compensation of BJT. The meaning of bias compensation of BJT is we know the collector current of BJT varies with change in temperature because IC is equal to beta into IB into 1 plus beta into IC naught into 1 minus e raised to power minus VCB by KT, and VCB is equal to VCE minus VBE. Your beta changes with temperature, VBE changes with temperature, IC changes with temperature. So, with increase in temperature, this increases, this increases, this decreases, this increases, this decreases, this increases. What I mean to say is collector current increases with increase in temperature. So, to compensate this increase in IC with respect to temperature, I can use two techniques. One is by using your bias stabilization, that is self bias circuit, and second technique is by using the non-linear devices. Non-linear devices are the devices whose resistance changes with change in temperature. So, very first technique I will be seeing this bias compensation, that is compensation in variation in collector current with change in temperature. The very first method will be by using diode in the BJT circuit, and second method I will be using the temperature sensitive devices such as the sensitor and thermistor. So, first I will talk about bias compensation using diodes, and second I will be using, that is bias compensation by using non-linear devices, that is thermistor and sensitor I will be talking about, right. So, let us see the first, that is first one. First we will be, I will be having two parts in first, that is bias compensation for voltage VBE. We know when you VBE changes, this will change, this will, if VB we know the voltage VBE reduces with increase in temperature, at which rate? Delta VBE by delta T, that reduces with increase in temperature, that is that reduces by this much value with increase in temperature, right. So, that circuit for this bias compensation is simple one. This is the circuit you have, plus VCC, right. So, what we do, we connect, basically we connect a diode in series with ammeter, and that diode is reverse biased like this. This diode is reverse biased. This is D, this is voltage VBE, this is voltage VD, right. So, this is voltage VD, and what will happen? This is compensation for VBE. So, with change in temperature, this will change and this will also change. So, BJT and diode both must have same material, both are made of same material. It cannot happen that it is made of silicon, it is germanium. If it is silicon, it has to be silicon. If it is germanium, it has to be made of germanium. So, both must have same material, and you know, you can see if this is voltage fall, this is voltage rise. So, both are opposing. So, your base current will be definitely proportional to change in VB and VD, or I can say, since collector current is function of base current, so collector current is proportional to this, and you can see if one increases, another also increases, net increase will be 0, right. Condition, the variation in VB and variation in VD must be same and that can happen only if the material of BJT and diode is same. That is known as bias compensation for voltage VBE. Bias compensation for VBE, and we know the voltage VBE is how much? 0.7 volt for for silicon, and it is 0.2 volt for germanium. Since it is larger for silicon, therefore the bias compensation for VBE is used for silicon transistor. Bias compensation is used for silicon transistor, right? So you should remember these are objective type questions for engineering services prelims, those who will be appearing next year, right? So there can be objective type question in engineering services prelims from this topic. Fine. So this is known as bias compensation for VB. Now I will talk about the bias compensation. You don't need to go for mathematical analysis. No one is going to talk about mathematical analysis, but you should know how to, what is the circuit and what is the purpose of the circuit. That's it. That is what you need to remember. Then I'll talk about the bias compensation for IC naught. The circuit remains similar like this. In bias compensation for IC naught, what we do, we connect a diode in the base circuit in reverse bias mode like this. So this circuit will be used for bias compensation of IC naught. This is IB, this is current I, suppose this is current I D naught, that is reverse saturation current in diode. So what will be IB? IB is nothing but I minus ID naught. Fine. And we know what is IC? IC is beta IB plus 1 plus beta IC naught, and you can please put this relation here. So this gives beta I in plus, this can be taken here, IC naught plus beta into IC naught minus ID naught. IC naught is in nanoamperes for germanium and microamperes for silicon. So when IC naught is in of order of nanoamperes, so this will not make difference, but when you multiply it by beta, it will make difference. So but IC naught is in microamperes for silicon. So this compensation is not used for higher value of the current, it is used for smaller value of the current when it is in order of nanoamperes, because this will not be affected much, this will be affected. So this compensation for IC naught is used for germanium transistor, germanium BJT, right? And if both diode and BJT are having same material, then increase in this will be same as increase in this, because both are reverse saturation current. This is reverse saturation current of the diode. Why? Because it is reverse biased. And what is IC naught? That is reverse saturation current in the collector junction. So this is your reverse saturation current in the collector junction from this side to this side. So if both are made of the same material, the change will be equal, so net difference will be 0. That's it. This is known as bias compensation for IC naught, bias compensation for reverse saturation current, which is used in germanium transistor. That's it. This is the only type of objective type question from this topic, that is bias compensation for IC naught. Now I will talk about the bias compensation using nonlinear devices, second one, right? And here I will be talking about two things, that is bias compensation using thermistor, and then bias compensation using transistor. So first, bias compensation using thermistor. Thermistor is what? Thermistor is basically, that is first I will be talking about. Thermistor is basically a semiconductor device having negative temperature coefficient. What is the meaning? Its resistance reduces with increasing temperature. So this is a semiconductor device having negative temperature coefficient. There are two circuits for bias compensation using thermistor. Let us see both circuits one by one. One circuit is this simple circuit. This is VCC, right? In this circuit, what we do, we connect a thermistor. This is the symbol for thermistor. We connect a thermistor here. That is the resistance of thermistor. This is thermistor. This is RC, R1, R2, RE, right? So let us see the mechanism. What will happen when temperature of the device increases? This is collector current, so this will try to increase. Collector current will increase because we have already seen in my previous circuits. So when temperature increases, IC will increase. But let us see what will be the role of this thermistor. When temperature increases, its resistance will decrease because it has negative temperature coefficient. When resistance of thermistor decreases, current in the thermistor will increase. So current IT will increase. This is IE. This is IC. So what has happened? Current IT is increased, current IC is increased, so current through the ammeter will increase. And due to increase in current through the ammeter, it has feedback in the base circuit. So, and base circuit, in the base circuit, this voltage opposes the base current. Base current is moving here, entering into this. So voltage across the ammeter opposes the base current. So base current will reduce with increase in VE. So when voltage across the resistance RE increases, base current will decrease. And when base current decreases, we know IC is what? Beta into IB. So IC will be reduced. I repeat, please understand. When temperature increases, IC will try to increase. So when temperature increases, IC will be increased. But when temperature increases, resistance RT will decrease. When resistance RT decreases, current IT will increase. When current IT increases, the voltage drop across IE increases, and when voltage drop across RE increases, the base current will decrease, and we know IC is what? Beta into IB. So that results into reduction in collector current. So collector current, which was trying to increase with increase in temperature, will decrease with increase in drop cross RE. That is how your tendency of increase in collector current with increase with temperature is reduced. That is known as bias compensation using thermistor. That is one technique. Second technique is, instead of connecting the thermistor here, what I do, I connect the thermistor here. This is the thermistor now, opposite to this. By connecting negative temperature coefficient here, or by connecting positive temperature coefficient devices here, we will see that later. Fine. So let us see what will happen. It's also interesting. As temperature increases, what will happen? I have already seen, as temperature increases, IC will increase, right? But please see this. When temperature increases, this is IT, say this is I, this is IB. So IB is equal to what? IB is I minus IT. IB is this current minus this current, if you apply KCL here. So as temperature increases, IC will increase. But as temperature increases, resistance of the thermistor will decrease. And when resistance of the thermistor decreases, current through the thermistor will increase. So as this increases, resistance of thermistor will increase, current through the thermistor will increase. Resistance through the thermistor will decrease because it is a negative temperature coefficient device. So what will happen? As IT increases, base current will decrease, assuming that this resistance is not changing and current through this is same. IVB is also same, right? So when IT is increasing, when this current is increasing, IB is reducing. So therefore this results into reduction in base current, and when IB reduces, what is this? IC to beta into IB, and that results into reduction in IC. So the tendency of increase in collector current due to temperature is opposed by this thing, This is the bias compensation in your using thermistor. But remember, if there is resistance here or not, that is not affected by this. Voltage drop is not taken into account. So, this type of circuit can be used in both self biased and fixed bias circuits, but that circuit, that thermistor here was can be used only when RA is connected. So, previous circuit is used for bias compensation of only self bias circuit, but this can be used for both self as well as fixed biased circuit. That is it. Now, let us see the another technique, that is by using transistor, right. Let us see the transistor. Now, transistor is what? Transistor is again a temperature sensitive device like thermistor. The only difference is thermistor has a negative temperature coefficient, that means its resistance reduces with increasing temperature. But in case of transistor, it is opposite. The resistance of transistor increases with increasing temperature. So, that is positive temperature coefficient. So, there are two circuits for this as well. Let us see the circuits. One is you connect transistor here. I am again indicating it like thermistor only. So, that will not affect at all. This is transistor now. This is transistor, right. This is VCC. This is IB. This is current through transistor, this is I, right. So, IB is equal to what? The current through transistor minus I. Now, let us see the effect of temperature here. When temperature is increased, this current IC will try to increase. So, as temperature increases, I will say as temperature increases, IC will increase. That is the simple expression we have seen, that is the simple phenomenon. But when you increase the temperature, the resistance of transistor will increase. Why? Because it is positive temperature coefficient device. Its resistance increases with increasing temperature, even though it is a semiconductor device. A semiconductor has a negative temperature coefficient, but here transistor has positive temperature coefficient because it is very heavily doped. When semiconductor is very heavily doped, its temperature coefficient become positive. So, that is the device, semiconductor device with positive temperature coefficient, right. So, when temperature increases, its resistance will increase, and when its resistance increases, current through the device will decrease. And we know what is base current. Base current is what? IT minus I. So, when it is reducing, base current will reduce. When it reduces, base current will reduce. So, as temperature increases, current IT will decrease, therefore, current base will decrease, and we know IC is what? Beta into IB, that will decrease. So, that what I mean to say is, when temperature increases, it will try to increase, but when temperature increases, the resistance of thermistor increases, current through the resistance of transistor increases, current through the transistor decreases, IB decreases. IB decreases means current IC is function of IB, so IC decreases. So, your effect is nullified, compensated on collector current. The effect on the collector current is compensated. This is the bias compensation using transistor. Another possibility is, what is the another circuit? This is simple potential divider bias, and I connect transistor here. Let us see what will happen. When temperature increases, its resistance will increase, and when its resistance increases, voltage drop, which is negative feedback in the circuit, will increase, and when negative feedback in the circuit increases, it opposes the base current, you can see. So, base current will decrease. When base current decreases, you know IC is beta into IB, so IC will decrease. I repeat, when temperature increases, IC will try to increase. That is one phenomena. But when temperature increases, the resistance of transistor will increase. Voltage drop across transistor will increase. This voltage drop opposes the base current. Therefore, base current will decrease. Decrease in base current is what? Beta into IB. So, collector current will decrease, and that increase in collector current due to temperature is compensated by decrease in base current. So, this is your temperature compensation or bias compensation using transistor. So, this is all about compensation, but this topic is purely important for engineering services prelims question. There is very little possibility in GATE and in engineering services mains. So, this is all about the bias compensation. Thank you very much for watching the video. In my next video, I will be talking about the thermal runaway and thermal stability of the BJT. Just wait for my next video.